Hello and welcome to a BESTdata video. This one we're going to be looking at how to use virtual channels to calculate differential currents and to find both operate and restraint current of a differential element. This type of math can be used for lots of different things. Differentials just happen to be one of the places where relays use a lot of internal math functionality in order to normalize and balance things out and create predictable protection. This particular example, I've got, again, multi-winding transformer. Let's say a high side and a low side. If we look at the settings, this happens to be BE1 flex. I've got a zone with two sources, 1999 CTs and 166. The transformer on the 199 side is a Y and a delta, DAB, on the 166 side. Polarity is set to normal. It has to do with CT polarity, so I don't have to do any flipping, but we could do that in BESTdata also if we wanted to. Taps are 2.79 on both sides, and I do have a different CT ratio, 60 on one side and 240 on the other. The CTs are connected Y. So all of this compensation is stuff that the relay is doing internally, and because the relay, the BE1 flex, is recording the raw values of what's actually measured, we can do that same math in BESTdata to reverse engineer and pull out all those different little pieces. I've already set them all up here, but we're going to go through the math to show you what we're doing at each particular step. Circuit 1, by the way, is going to be 166, circuit 2 is going to be 199, and the R is going to be the restraint current. So these are the compensated values. If I'm looking at the instruction manual, the compensated values are going to be dependent upon how those transformers are connected as well as CTs. There's an excerpt in the BE1 Flex manual that goes through some of the description. Very generically speaking, the most basic example is if you have a Y delta transformer, just a two-winding transformer, for example, you're going to compensate the Y side because the delta side doesn't have neutral readings, so you have to compensate the Y side in order to match it to the delta. This table, again, 38-5 in the instruction manual, does talk through all sorts of different combinations, but in our particular example, we're going to apply delta compensation to the Y side, so the 199 side, and also we need to put in the square root of 3 factor. So a couple of the pieces that we're going to do that you're going to see, we're going to take the delta compensation, so our compensated current of A is going to be IA minus IB, and also include the square root of 3 as well as CT ratio and tap factors. So now when I go ahead and look at what's been configured, I can go ahead and look at that circuit 1 that's been already compensated and mathematically calculated, and I can look at the math. So I take that 199, the raw current, I subtract out current of B, so that's A minus B. I take 173, that is the square root of 3, I divide it by the CT ratio or the CT multiplier 60, and finally 2.79 is that tap value. So that's what I have to do to create the restraint current of channel A. I do the same for channel B and C, and B minus C, square root of 3, tap, CT ratio, and tap. Now when I get down to circuit 2, this is the 166 side. This was the delta side of my CT. This one's cleaner because I don't have to compensate it for that delta AB because it's already compensated mathematically by the transformer and the measurement. So I just take the CT ratio, the current channel that I'm looking at, divide it by the CT ratio, and also divide it by that tap factor. Now I get all these pieces set up, and I get the restraints of A, B, and C on the 166 side, on the 199 side as well as the 166 side. The last piece I'm going to do is calculate the operate current. Differential elements are looking at operate and restraint. And again, we can go into further detail if you need to know more on operate versus restraint and how differentials work. But just generically speaking, we're going to take the restraint current of one circuit, add it to the restraint of the other. And by the way, this is an addition because I'm assuming that the polarities are opposite of each other. If I look at my settings and determine that these polarities are flipped for whatever reason and look in the same direction, I would just do a subtraction in this math instead. So once I create that operate current, I'm going to take circuit 1 plus circuit 2, and ideally those should equal 0. In this particular example, I see that I actually have quite a bit of operating current, and if I hover over this, it's varying quite a bit. What actually happened in this particular example is there was a CT wiring, a mismatch. So what we're able to do with BESTdata is reverse engineer. Let's say hypothetically if I change this wire, flip the polarities, I can magically go ahead and do a correct wiring and do that math and manipulation within the software, and I see my operate currents flatten out fully. The way we did that from a manipulation standpoint is instead of doing, channel A minus channel B, or such and such as a typical compensation factor, we can manipulate and use these channels and do that internal math to make it work out. So again, in this particular case, it was C minus A, which is the correct differential, compensated differential value, and then I also had to put a -1 in there, again because of all that compensation due to a polarity flip as well. So numerous CT wiring errors, but what it allowed us to do is actually prove that these wiring changes were exactly what was needed to balance that circuit out. So again, lots of things that we can do in the configurable. Knowing how to utilize these mathematical values is the important part. Thank you for joining, and come back for more videos later.